the next video for Further Math Year 1 Core Chapter 7. I think I'm going to split this one into several videos. I'll do a few examples, otherwise it'll be one long, big, unwieldy thing. So we're looking at reflections and rotations. And before we do, I just want to talk about the unit square. The way to consider these transformations is to consider the effect they have on the unit square. So here's a unit square. It has sides of length 1, and let me just put these points in. And the reason that we use the unit square is because if I apply a transformation matrix, let's call it T, I'm going to apply it to 0, 1. No, I'm not going to apply it to, 0, 1, 1, 0. So 0, 1, 1, 0, that point there. Let's write it the other way round. 1, 0, 0, 1. Sorry, I'm going to start. I won't start again. Apply it to that side and that side. Well, that's the identity matrix. And so if I apply a transformation to these 2 points at the same time, well, I just end up with the transformation matrix. So I can know what the transformation matrix will do to the square just by looking at the matrix, or if I've done a reflection or a rotation, I can say what the transformation matrix was. What I do is I consider the two sides of the unit square, and drawing them in different colours is a really useful thing here. Let's say I'm going to apply this transformation, 3003. Well, I know that if I apply it to the unit square, I just end up with 3003. So this is not just the transformation matrix, this is the end coordinates. This is how each of these 2 points got transformed. So 1001 gets transformed to 3003. Okay. So 1001 turns into 3003. 1, 2, 1, 2, 3. Sorry, that one needs to be blue. So we can see it's actually an enlargement. There's the rest of the square. We can see that 3003 is an enlargement, scale factor 3, centre of enlargement is 0, 0. Remember, with any matrix transformation, 0, 0 never changes. It's invariant. And we need to know these terms. An invariant point, 0, 0, is always an invariant point. We also have some invariant lines here. If you think about that line, that hasn't changed. That's y equals 0. That line hasn't changed. That's x equals 0. The line at the top of the square there, that has changed. That's not an invariant line. The line at the side of the square there, that has changed. That's not an invariant line. But the line through the diagonal, well, that's still the same. So for this transformation, y equals 0, x equals 0, and y equals x are invariant lines. Oops. Invariant lines. There's a lot more to be talked about with invariant points and invariant lines, But common sense says, looking at the diagram, they're the lines that haven't changed. Now, example 4 gives us, it just gives us the square. It says I've moved my units square. It's been, what has it? It's been reflected. So 1, 0 has been reflected to minus 1, 0. I'm actually going to draw 2 copies of it. So my unit square, 1, 0, 0, 1. There's the square. Has been transformed. Oh yeah, my black went out, didn't it? Has been transformed to minus 1, 0, 0, 1. There it goes there. Now, whether I draw it on separate axes or whether I sketch it on the same axis doesn't really matter. We can see that it's a reflection in the y-axis. And the transformation matrix then, or 1, 0 has gone to 0, minus 1. 0, 1 has stayed at 0, 1. So 1, 0, 0, 1 has transformed to minus 1, 0, 0, 1. So the transformation matrix Q is minus 1, 0, 0, 1. It's just the matrix of where each of those 2 points has ended up. The invariant lines, well, the horizontal line y equals 0 is invariant. The vertical line x equals 0 is invariant. And of course, that top edge, the line at the top edge of the square, is also invariant. So invariant lines, x equals 0, y equals 0, y equals 1, are invariant. Now we've got to be really careful here, because this could have been, I could get from that square to that square via a rotation. But of course it hasn't been rotated. Were it rotated, the red would have been pointing up and the blue would have been pointing across. So drawing those two sides in different colours and their corresponding sides in different colours really is important, because it shows the difference here between a reflection and a rotation. Let's look at example 5. So example 5, we're given the transformation matrix. Hang on a second, I'm opening the problem blue book. So in example 5, we're given the transformation matrix and we're asked what the transformation is. Well, let's sketch it. I'm starting with 1, 0, 0, 1. There's the square. It's being translated to 0 minus 1. 1 minus 1, 0. It's been transformed, so not translated, it's been transformed into that. Now, that is not a rotation, because if it was a rotation, my red side would be there and my blue side would be there. You might find it easier to sketch it on the same graph. That's fine. Because of the colours, it's not a translation. I guess if you sketch it on the same graph, you really need to say which one's the object and which one is the image. I've just put A and A dash. Now I can see that this is a reflection in the line y equals x. So they gave me 0, -1, -1, 0. So I turned my 1, 0 into 0, -1. I turned my 0, 1 into -1, 0. And I can now see that it's a reflection in the line y equals -x. For B, I know that 0, -1, -1, 0 maps A, B onto 3 plus 2A, B plus 1. So of course if I multiply this matrix out, I get 0 times A minus 1 times B, so minus B on top, minus 1 times A, 0 times B, so minus A at the bottom. Oops, 3 plus 2A, B plus 1. So I have minus B equals 3 plus 2A minus A equals B plus 1. Solve them simultaneously gives me A is -2 and B is 1. So if I'm given a matrix, I can sketch the square and then I can see what the transformation is. If I'm given the transformation, then I can see where each side maps to and write down the matrix. So I need to be able to go both ways. Give me the transformation, write the matrix, or give me the matrix, write the transformation. I'm going to stop there and I'll do a separate video for the next two examples.